Good afternoon. This is going to be a quick video that demonstrates a little bit of physics. We're going to be looking at Phuket Word's video from April 17th, 2018, where he's demonstrating flat Earth physics with an apple on a scale on a table. I'm going to play his video, which is in the description below. We're going to start at about 1 minute and 14 seconds in, where he's talking about the weight of this apple in the medium of air on the scale. So let me switch the audio so we can hear him instead of me. We'll play the video, and then I will make my comments afterwards.
So we can see that this apple all by itself in the medium of air weighs 120.8 grams, 120 grams. There is no need to perceive that there is any external force pulling this unless you want to believe that we can stick to the outside of a spherical Earth. Otherwise, we just see it as it is. It is a solid object that has a weight of 120 grams. Yes, you can call that weight a force, a downward force if you want. You can call it gravity if you like. That gravity just means weight. And what has happened with the Newtonian language of physics is that weight has been turned into or translated into a force, but we are told it is an gravity, if you like, created by the specific mass of the spherical Earth, which pulls everything towards it, so that we can perceive that we can stick to it. Yeah, but really it is just the weight of the apple as a dense object in the air, which cannot support it. Okay, it weighs 120 grams. On this table here, the table is just a solid object. It's not putting up any force against the apple. It's not opposing gravity. It is just stopping the apple from going down any further. Of course.
So it's the comments that he's made here that I find need correction. He's explaining that because of the medium of air that the apple is in, when it's placed on this scale, it gives a reading of about 120.8.9 grams. And when he places the apple on the table, he says that the table is not applying any force to the apple. The table is simply stopping the apple from moving, from going any further. And so I ask a question here, which has never been answered by Phuket. He says the table is not applying any force to the apple. It's just stopping the apple from going any further. My questions are, why would the table need to stop the apple? Does the apple want to continue going downward? If something wants to continue going downward, how do you stop that? By applying a force upward equal to that downward force? There are no good flat Earth responses here. Chris says the ball applies force to the table, not the other way around. What's stopping the table from going down? The table is pushing down, not up. And my response here is, Phuket Word says the table is stopping the apple from going any further. This implies that the apple wants to go further down. How does the table prevent the apple from succeeding in going further down? So before we go on with that, how does the apple want to continue going down? The reason the apple wants to continue going down, as we all know, is the gravitational force of the Earth. The gravitational pull of the Earth is pulling the apple towards its center of mass. It's this pull which gives us, at whatever elevation Phuket Word is at, it gives that apple its weight of 120.8 or 120.9 grams. It is not because of the medium of the air that it is in. If he were in denser air, perhaps the change that we would see is that the air pressure plate pushing down on the plate would be slightly more or slightly less depending on the air. But more importantly, it would be the gravitational force which is different with elevation. If he were to perform this test in a vacuum, he would not see a noticeably different weight for the apple. What is the combined weight of the air in the room that he's experimenting in? Surely it's a negligible value, or else we would always do all of our weighing in vacuum chambers. If really the force of the air around us was sufficient enough to affect these weights that we measure. So continuing then, consider that instead of a table, it's your hand the apple is resting on. The apple wants to go further down towards the ground, but your hand stops it. How does your hand stop the apple from going down further? Not simply by being there. Your hand being under the apple is not enough to prevent the apple from continuing to move downwards. We know this because if we were to place the apple with something that weighed much more, say a 300-pound weight, if we put a 300-pound weight in our hand simply being under the weight would not stop the weight from going further down. Our hand needs to exert a force upwards against the mass in our hand to keep it where it is. The apple is exerting a force down, and so your hand or the scale or the table or the ground must exert a force up. So when the apple is placed on the table is exerting a force up against the apple. When you try to use the flat earth physics of buoyancy and density, you run into the question of what is the density of this apple and what is the density of the table? If the density of the apple is greater than the density of the table, then why isn't the apple going through the table until it reaches something more dense than itself? Another place where density and buoyancy fail to describe the physics of moving objects sufficiently, even though we know that buoyancy includes gravity, but you'll never get a flat earther to actually give you an equation for buoyancy because they'll have to give you something with gravity in it. That's besides the point. But if air near the surface of the ground is more dense than air higher up, then that means an object falling through air is continually moving into a denser and denser and denser medium. And one would think that if all we were dealing with was density and buoyancy, the buoyancy of an object in a very what we end up coming into is if the object is moving into a more dense medium, if the medium it's in is growing denser and denser as the object moves, shouldn't the object experience a deceleration rather than an acceleration? But we know that unless we encounter drag, an object falling to the ground accelerates at a known rate. We do not see that object accelerating and then decelerating as the medium it is in, the air, gets denser and denser. The only time we see that is when there is sufficient drag on the object due, once again, to gravity, but also due to the orientation of the object as it moves through the air. So that's all I wanted to do. You can watch Phuket Word's ridiculous video. I don't think it's a shining example of flat earth physics in the sense that it doesn't actually try to explain real world events, real world situations from a physics model. But you can watch the video to see how he attempts to use density and buoyancy to explain, for example, the weight of an apple. But that's all the video for today. Enjoy the rest of your weekend. I have a new equatorial mount, which I am keen on using, and I hope to get a good look at Mars and Saturn and Jupiter and maybe some deep sky objects tonight. Thank you again.